sharing. Okay, so today's lecture, we have two parts, actually 3 parts to be precise. I want to finish up what we were discussing about two-manifold, and then we're going to move on to actually a bit more towards machine learning again, but with a more focus on kernel methods. The reason I want to do that is because one way to interface sort of persistent diagram or barcode with machine learning tasks is to try to turn the persistent diagram or barcode into some form of vectors, or to use some sort of kernel methods so that they behave better. Okay, I will explain what I mean by better later. But the idea is there's a bunch of kernel methods from classic machine learning. We're going to start reviewing that and then move on to talking about kernels over persistent diagram. So, okay, what do I mean by kernel? Our kernel is just a measure of similarity that satisfies certain conditions for well-behaved kernels. And we're going to talk about how do you have, there's multiple versions of kernels that can be defined over persistent diagram. And we're going to go review a few of them. But let's first finish the discussion over manifolds because, you know, in some sense that this is sort of the underlying assumption over some of the point cloud we work with. And we specifically just focus on two-dimensional manifold. Okay. So as I mentioned before, from the last class, there is a way to actually construct two-dimensional manifold. It's by kind of gluing, you know, some sort of basic unit. What are the basic unit? The basic unit are like sphere and torus. So for example, if I want to get a double torus, you see this notation here, which is this sharp notation, which is basically this sharp notation means that it's a sort of a connected sum of those two. What do I mean by that? In order to create a double torus, I'm going to take two single torus and kind of chop them off at the boundary and then glue the boundary together. And that's how you create a double torus, okay? And the idea of this is this classification theorem is to say that for all the compact two-manifold without boundary, there's essentially two families of them. And those two families are constructed from basic unit of orientable two-manifold and non-orientable two-manifold. One is coming from, say, a sphere and then sort of those sum of torus. The other one is coming from projected plane, which is a non-orientable manifold, and the sum of them. And then when they say they exhaust the entire family, that means all the two manifold can sort of be classified as coming from one of those two families. Okay. So what do I mean by that again? Is that, you know, let's go back to looking at, you know, what is this language say? Another way to describe it is to say, okay, all the connected closed surfaces, you know, as this two manifold means, surfaces here means two manifold, is going to be similar to one of those three families. Either it's a sphere, it's a connected sum of tori, or it's a connected sum of real projected plane, okay? So let's look at like those simple unit and how are they formed. And one of the way to study them is what's called a polygonal schema. And what that means is that I'm going to try to describe those basic unit, which is torus, sphere, and real and projected plane by gluing different sets of things. So I have a piece of paper today that I can denote what I mean by that. So let's say I have this rectangle. If I want to form a torus, I'm going to glue the top edge A and the bottom edge A by following the orientation. So it's like this. So now you get, you know, a cylinder. And then you glue left boundary with the right boundary, which is a B with B. Again, following the orientation, not the most perfect ones, but you could imagine I kind of do it like this, where the end point has to glue together. And that's create the torus, okay? And then if I want to create the sphere, I'm kind of folding B against B over here. As I said before, is like folding a dumpling together. And once you do that, that's create a sphere. And then the projected plane is the one that's really interesting, is when you glue the top edge to the bottom edge, you have to, I can't, of course, recreate it because this is not orientable. So I kind of have to twist. Let's see, what do I mean by twist? So one way of this twist is when you're creating a Mobius strip. When you're creating a cylinder, right? I kind of glue the endpoint together, following the orientation like this. This is where the cylinder is created. But when you create a Mobius strip, and let me make it even more. When you want to create a Mobius strip, you want to rotate the endpoint one rotation, and this is your Mobius strip, okay? But if you just do this, this is only one edge of it. The other edge of it has to be also rotate, which I cannot recreate, but that's what gives you a projected plane, okay? And finally, the Klein bottle, which is a classic example, is that you go from top to bottom as you're gluing an initial cylinder, but then you kind of rotate the other side with left and right. And then when you see this, this is a typical picture of a Klein bottle, okay? And it's what's interesting is the Klein bottle is essentially a fancier version of the Mobius strip. Because if you think about a Mobius strip, okay, a Mobius strip in this lower corner here is that if you have an end that walks around the Mobius strip, it's going to go over all faces, right? It's going to travel all the surface area because it's kind of, there's no separation between exterior surface versus interior surface. The Klein bottle has a similar phenomenon where if you put a little end over the surface of it, and then as the end is moving, okay, then what happens is that that end is going to touch all the surfaces. But what's interesting about it is actually Klein bottle is to glue two Mobius strips together, right? So what did that mean? One thing that, as I pointed out, if you look at the Mobius strip, first of all, let's look at the cylinder. If I have a cylinder, how many boundaries do I have? Cylinder is a manifold with boundary, right? So yeah, go ahead.
There are two boundaries.
Yeah, exactly. There's a top boundary, and then there is a bottom boundary, which of course, there's two pieces of the boundary. But if I am focusing on the Mobius strip, there's only one boundary. Because as I'm going, this is going to the back end, and it's going to come to the front end. So if I take the boundary of the Mobius strip, it's one single loop, okay? What does Klein bottle do? Klein bottle is actually taking two of those Mobius strip and then glue them along their boundary. And that's what you get as a Klein bottle, okay? In the next lecture, I'll show you a hat of a Klein bottle hat. I think that's what all topologists or computational topologists have, is having one object in the home that is some form of Klein bottle. All right, so now there's a question of why do I even tell you about this Klein bottle other than, you know, mathematical curiosity? It turns out there's a 2008 paper who basically said that they believe the natural image patches from, well, I say if I take a bunch of nature images, like say I take a picture of a forest, I take a picture of, you know, the mountains and so on and so forth. And when I take the patches, so what do I mean by that? So let's say I have a picture of the mountain, very simple picture of the mountain. Maybe there's a lake in front of it. Okay, this is a picture. And then when they do is they actually take those small patches. Let's say it's a 3x3 patch by pixel, like this is a patch of it. If they take a bunch of those patch from a many number of natural images, what they claimed and conjectured is actually those, if I treat those each of those patch as a point, and I treat the whole thing as a point cloud, if I study the homology of it, it has a homology of a Klein bottle. Okay, so that's where Klein bottle actually shows up in real world like data analysis. Okay, so and also, why is this patch interesting? Is because when you study convolutional neural network, one of those things that convolutional neural network do is by treating an image into patches. So understanding the topology of input image is actually really interesting. It's because, because neural network is using those patches to try to extract features for classification tasks. Okay, so that's one place Klein bottle shows up in data analysis. Now, I have described to you a collection of two-dimensional manifolds. So I now want to give you an idea of their Betti number, right? And in fact, one aspect where, as I said, when the folks believe the space of natural image patches form a Klein bottle is by studying the homology of the point cloud formed by those patches. So, okay, so we've seen some of those objects before. If I have a circle, it has one connected components, and it has one loop, right? So that's Betti number, but it has no void. A sphere, I'm going to try to draw it. This is a sphere. It has one component, no loop, but it has one void. A torus has one component, one void, right? Because there is an inside versus outside. And there's two loops. By now, you should be somewhat familiar with what is two loops. This is a first loop. This is a second loop of the torus. So it has two loops. So Betti 1 is 2. So Betti number is 2. Now, the interesting part is about the projected plane. So remember, why if you think about projected plane, it's one of those non-orientable things, so which means that there's no separation. If I put an ant on it, there's no separation of inside outside. So intuitively, the projected plane has one component still, but it doesn't have loop, nor it does not have void. The Klein bottle is the same thing. This is a really interesting part. The Klein bottle don't really have a void because, as I mentioned before, if I have an ant that moves around in the surface, it's going to go into the interior in a smooth way, which means there's no separation between interior and exterior, which means there's no such thing called a void, a two-dimensional void. Okay. So of course, Klein bottle does have a loop. Of course, I'm trying to picture it. It's not the best picture, but the loop looks like here. Okay. And so now it's the next thing. If I have two-hole torus, and I think we kind of revisited before, this is my two-hole torus. And we argue that it, of course, have one component, one void, but it has 4 tunnel. There is the obvious, the donut hole. And then there is a loop here, and then there's a loop here. Okay, and turns out if you have a G-hole torus, where G means the genus, which I'm going to define very soon, is that the number of loops it has is 2 times the number of genus. So essentially what happened is, you know that the torus, the regular torus, this is G equal to 1, and this is G equal to 2. And remember, the G-hole torus is a gluing of multiple individual torus. So basically, each time I glue one, I increase the number of loops by 2. So there's this formulation, which is saying that if I have a G-hole torus, then I have 2G number of loops, or dimension 1 homology in my space. So what do we mean by genus, right? Genus of a connected orientable surface is an integer representing the maximum number of cuttings along a non-intersecting closed simple curves without disconnecting the resulting manifold. So earlier this semester, I kind of gave this definition, but now since we have a better understanding of two-dimensional manifold, here is what we have. So if the sphere has a zero genus, is because if I cut it along a non-intersecting closed simple curve, I would disconnect the manifold, right? Another way to draw it is pretty much if I draw a curve like this, I'm chopping off a slice of my sphere. Now, the torus is a genus 1 is because if I take one single cut like this, I should use red really. I'm not disconnecting it. But if I do one more, I'm disconnecting it. So the maximum number of cut I can do is 1. So for the genus 2, which is torus, a double torus, if I cut it here and here, I'm not disconnecting it. But if I do one more, I'm disconnecting the surface, and so on. So the genus 3, you have a different way. You can have, for genus 3, you can glue it also like this, right? Or what it showed here. Either way, there's maximum 3 cut I can make without disconnecting it, okay? So there's an interesting thing related basically with the genus of my orientable surface with respect to the Betty 1, the rank of dimension 1 homology clause. Okay, so before I switch to other topic, remember 2 lectures ago, we gave a demo of a few open source thing, and I'm thinking about a possible sort of bonus project will involve the open source implementation of a mapper algorithm. And I know it also might be useful for your final project. So this is a list of some of those existing sort of implementation of mapper. But if you actually go to Mapper Interactive, there's a paper, and that recent paper also has a review of other open source implementation of mapper algorithm. Okay. And another interesting example is, Faye didn't go into all the details, is, for example, in Kepler mapper, there's a number of default examples that you can play with, including the breast cancer example from one of the previous research work. So, so it will be interesting to play with those examples. All right, so to end my discussion over torus, I've been careful of what's called, of describing what I mean by torus and double torus. So a double torus is the one where I glue multiple torus together. There's the definition of 3 torus, which I want to differentiate so this is not equal to the one I just drew, which is a torus with 3 holes. Okay, this is not. So this is actually means something different. So what happened is a 2 torus, a 2-dimensional torus, is you're gluing the top edge with the top edge and left edge with the left edge. But it can also be described topologically. So T of 2 can be described as, this is a 2-dimensional torus, is topologically looking like 2 spheres multiplying them together. Okay, so it's basically the product of a circle multiplying itself. Okay, so how do you imagine that? What does this multiplication do? You start with one loop. So a loop is S1. Okay, that's basic. Well, actually, I should really draw it very nicely, but it's fine. A loop like this is S1. When I say this product, what I mean is I start with a loop, and when I do the product, I kind of turn the loop around in one loop, right? So it's essentially you start with, I would really like to draw it. If you think about a torus, what it's doing, it's starting with this loop, and then you move this loop around along a separate loop. So if you move this loop along this green path, it will trace out the entire surface of my sphere, so of my torus. So this is what you get when you say, I am doing the product of these two. Okay. So now the three-dimensional torus is the product of three copies. So the three-dimensional torus is now S1 times S1 times S1. So what do I mean by that? I will start, oh, this is a typo, sorry. I will start with S1 and I multiply one copy of S1 on top of it. So you know that I'm taking the current space and I kind of rotate it in a circle, and that will trace out the surface of my two torus. Now, if I want to do another copy of it, okay, what that do is I'm going to take this entire space, which is already two copy, and rotate that among a circle of S1. Okay, so that's what three torus looks like. And what's interesting is that if you have a three torus like this, there is a corresponding Betti number, meaning that it has one component, it has three tunnel, it has three void, and it has one three-dimensional void. Okay. Again, this is hard to imagine, but why do I even mention that? Is because three torus actually comes from a lot of network topology when I try to connect networks. Okay, so let's say each of those cube in this picture is a particular computer, and I'm connecting those computers together to form a grid. A three torus is going to come in when my grid is connected this way. Okay, this is in a parallel computer system. This is where a particular three torus will comes in. Is that, you know, if I take, for example, a slice here, right? You know that the left edge is connected to the right edge, the top edge is connected to the bottom edge. But then if I take the whole thing, is that there's a third dimensional connectivity, which is precisely this third component. Okay. So in a way that three torus is one way to imagine three torus is you can think about taking a cube where the top face is mapped to the bottom face, the left face is mapped to the right face, and the front face is mapped to the back face. Okay, so that form of connectivity is where the three torus shows up. Okay, this is what I'm showing in this picture is trying to tell you all the blue edge in this picture is connecting the front face to the back face, right? So all the blue edge is connecting the front to the back. All the red edge is connect from left to right, and all the green edge is connecting from top to bottom of this cube. Okay, so that's where three torus shows up. So then the rest of it is purely out of curiosity, is how do you actually study a mapper representation of a three torus, okay? And which filter function you use. So I would really like to play this. Let's see if I have a YouTube. Do I even have YouTube? That's YouTube TV. Oh, actually, no, that's not actually what I should be doing. Why did I do that? Okay, here, this is what I should be doing. Okay, so this is a visualization of how 3 torus, a flow in 3 torus looks like. So the edges is basically looking at how things are connected. And the reason why I want to show you this video is, remember I said 3 torus has 1 component, but it has 3 loops, and it also has 3 void. At least this visualization is to try to show you where the 3 voids are. Okay. It also has, yeah. So this is in some sense the best we can do. It's essentially it's taking a torus and wrap around itself in a circle again to create this 3 torus. So this is just a visualization of it. And then if I want, right, if I want to study it further, this is another visualization of people trying to take the cross section of the 3 torus to try to study it. So if I go back to the question, like, you know, how do I want to understand the topological summary of a 3 torus using, say, mapper, then one idea is maybe taking slices of the 3 torus and compute the topological summary of it. Okay, but this slice, it's quite interesting. For example, especially this particular slicing of it, it's trying to show you there's multiple voids in this multiple 2-dimensional voids. There's 3 2-dimensional voids in the 3 torus. Okay, and then this at least shows this actually shows all 3 of them. So if you see, there is a void right here, there's a void right here, there's a void right here. Okay, so it's a very interesting object, and I think there's a lot of, you know, interesting, curious things you can ask about such object. And it's also one of those objects that is easy to define but very hard to imagine. All right, so that's it. What I want to say about manifold. I would like to shift to talk about kernels.
I have a question.
Yeah, go ahead.
So if you take something like the Klein's bottle and just sample a bunch of points on the surface and run Rips complex on that, would I still get the correct H1 features?
You will get the correct homology.
Okay.
Yeah, you can try it. In fact, like I said, this particular paper, when they said, this paper, sorry, it's at the end of the reference. This paper on the local behavior of the space of natural images, they basically treat the patches at the point cloud and compute the homology of it. Okay. But remember, when you run Ripser, there's a little bit tricky thing because Ripser is looking at the filtration of it. So you're actually computing persistent homology. So you need to kind of decide on what is your end radius parameter or diameter parameter you want to choose. Remember, if you choose that too high, then everything is going to become connected and you're not going to detect some of those homology at the end of the filtration. So you might want to try several parameters.
Okay.
Yeah.
Like what I was thinking was, you know, there's that point where the bottle sort of went in on itself.
What do you mean?
So like in the Klein's bottle that you showed,
Yeah.
there's this bit at the bottom and sort of tunneled back into itself.
Yeah.
So there are going to be a bunch of points like on the circular disc right over there. So wouldn't that sort of interfere when you're doing the whole?
No, first of all, I have not told you how to sample from it. And I don't know if there's a good way to sample from it, right? But remember, this is an illusion right here, because this is sort of trying to create a visualization. And if you look at this, this is actually not exactly what Klein bottle looks like because they don't have this hard intersection here. Because this is trying to embed a Klein bottle in 3D.
Okay, so these are 4-dimensional points.
Yes, well, Klein bottle is something that don't have a good embedding in 3-dimensional space. So yeah. Okay. So my best bet for you to have a really like a point cloud sample from a Klein bottle is based on this paper, because they say that some of those patches from natural images really form Klein bottle. So one way to kind of have point sample from Klein bottle is looking at the patches of natural images.
Okay.
And then remember the barcode for Klein bottle is 110, meaning that it has one component, one loop, but there's no void.
Okay.
Yeah. All right.
So, can I ask one question? So do we still use Z-mode coefficient for Klein bottle and projective plane?
Yeah, you can.
Then otherwise, the Betti numbers would be different if we still use Z-mode coefficient. I think the Betti number for the first and second should be boosted by 1.
So yeah, okay, so in this class, I'm only talking about integer coefficient. But you can try, and I don't remember if Ripser does, you have to double check. I don't remember if Ripser has non-integer coefficient for computation, but I know Dionysus, hopefully I didn't abuse it. I think there's some open source software that does go beyond integer coefficient.
I mean, isn't the default integer coefficient we are using is Z-mod 2Z?
Z2.
Which is Z2.
Yeah, which is Z2. I mean, we could take, for this class, we're mostly focused on Z2. But later on, when we talk about time-varying data, there is a cohomology parameterization there. And in there, we're not using Z2 coefficient. And that's a little bit detailed later that I will describe.
Thank you.
Yeah. Okay, so I definitely want to do this example, but I actually think this is a good time to break. And I want you to kind of remember at the end of last lecture, I want you to do a take-home example of computing homology by hand. And remember, computing homology require doing a reduction of multiple matrices. So I want to go through a complete example, a little bit more complicated example than the one I did last time, so that you have a good understanding of it. But this is a good time to take a 5 minutes break. And you can try to do it yourself. Basically, what you want to do is to reduce 3 different kind of boundary matrices, which is sigma 0, sigma 1, and sigma 2 by hand. And then using this formula here to look at the rank of the matrices and then induce the Betti number. But when we return, we're going to do it together on the iPad. Okay. All right. So 5 minutes until 9:50. All right, let's get back to this. Okay, so let's do this together for this example. Okay, so this is a space that is basically a surface of a tetrahedra, okay? So we know that, without computing it, we know that there's one component, there's no loop, and then there's one void because it's a surface of a tetrahedra. So it has all the triangles, but it doesn't have the tetrahedra in the middle. So what we want to do is to reduce the boundary matrices through Smith normal form, and then read off the rank of it. Okay. So let's be very precise. Once you have a reduced matrix, the number of empty column is, if your current matrix is dimension P, then the empty column is a rank of ZP, which is the rank of all the cycle group. And then the number of non-empty rows are the rank of the boundary group, but one dimension lower. Okay. But let's make it very precise. What are the matrices I'm going to deal with? First of all, I'm going to deal with zero-dimensional boundary matrix. So zero-dimensional boundary matrix is sigma 0, and then the columns are A, B, C, D. The columns are just the vertices. And then the rows are basically 0 because the boundary of vertices is 0. There's nothing I need to do in terms of reduction. It's already reduced. And now remember what I said, that the number of empty columns, right? The number of empty columns is the rank of the cycle group. So the rank of Z0 is 4. So rank of Z0 is 4. Remember also the rank, the number of columns is also the rank of the zero-dimensional zero-dimensional chain group right here. Then the rank of the chain group, C of 0, is equal to 4. And then the later part is not surprising because how many columns I have corresponding to how many independent elements I can use to construct zero chain. Remember, zero chain is linear combination of vertices. There's 4 unique vertices. So there's ways to use those 4 elements. That's why the rank is 4. Now I'm all done. I'm not doing any reduction. Now I want to do the first one. And this is one that requires some effort. The first one, this is first dimensional boundary matrix now. So when I talk about first dimensional boundary matrix, the columns are now edges and the rows are vertices. So there is a total of 6 edges. So I'm going to do the edge AB, the edge AC, the edge AD, BC, BD, and CD. Those are the 6 edges. And then I want to take their boundary. So I want to take their boundary of vertices. So there's 4 vertices. So the boundary of AB is, of course, AB. The boundary of AC is A and C. The boundary of AD is A and D. And PC, BD, CD. Okay. Now I need to reduce this to Smith's normal form. So this is where I'm going to try to copy. And I'll put another page. So now remember, I just want to reduce this. Ooh, okay. Okay. So now my operation is I want to reduce it to Smith's normal form. What does Smith's normal form do? Remember, I need to zero out all the zeros at each one. So there's a bunch of ones along the diagonal and the rest is 0. That's a Smith's normal form. So remember what I did last time is I'm going to first zero out what's below each of the column. So I'm going to do the zeroing out each column below the ones first. So I'm going to use a different color. Now I start with the first column. And first column, I only want a 1 in this position. So I want to keep this 1. And then what I want to do is I want to zero out anything below it. In order to zero it out, I just need to add the first row to the second row. I'm using this arrow to say it's an addition operation. So now I'm just doing row operation. I'm adding rows onto each other. So I'm adding the first row onto the second row. So what I do, 1 plus 1, I cancel out, and then I carry 1 and 1 in there. That's what I did. So now I have 0 out everything below this. I'm good. Now, in order to move on to the second row, I would like to keep this 1 in this current box, but I want to 0 out what's below it. So in order to do that, I'm going to add the current second row to the third row. Right? So I add my current second row to the third row. That means 1 plus 1 is 0, and then 1 plus 0 is 1, and 1 plus 1 is 0, and 1 plus 0 is 1. So that's what I get. Okay? So now I have everything below it to be zeroed out. Okay, so I'm going to erase this to reduce complexity. Now I'm going to do the third column, and I'm going to do the same. I want to keep the one on the diagonal because this is the one on the 3, locations, third row, third column. I want to keep this one, but I want to zero out everything below it. And again, I'm going to do is I'm add the third row, the current third row to the last row. And what's interesting about it is that actually when I do this, 1 plus 1, I cancel out, 1 plus 1 cancel out, 1 plus 1 cancel out. So in effect, I zero out the entire thing. So through row operation, I kind of zeroed out part of my matrix. Now I need to proceed with column operation, okay? So column operation, I want to make the first one, the one I'm going around, to be the unique one on its row because I want a diagonal shape, right? So now what I need to do is I need to add the first column onto the second column, okay? So when I do that, 1 plus 1 is 0, so I cancel it out. Same thing, I want to zero out the third column's first one, so I want to add the first column to the third column. Again, I zeroed out. I'm not done yet because I still have this one right here, right? So I add the second column also to the third column, and I zero it out, okay? Now, what I need to do is I would like to zero out the rest of my columns. And in order to do that, in order to zero out the fourth column, I just need to add the second column to the fourth column, okay? And then the 1 plus 1 is 0. In order to zero out the fifth column, I need to add the second column and the third column. Now it's easy because the second column and the third column is just a unique one in there, right? So you just need to add the second and then the third, and then you kind of cancel it out. And the last one, you just add the third column to the sixth column and you zero it out. What do I have now? This matrix has now been reduced such that there is 3 ones along the diagonal for the 3 columns, and then the rest is 0. So what do I have now is I have reduced this matrix to be a form that looks like, again, the same number of columns, same number of nodes, but it looks like 1, 1, 1, and then the rest is 0. I'm just going to write a few entries of it, but you know the rest is 0. So now remember, giving this the rank, the number of empty column is a rank of Z1. So rank of Z1 is now 3 because it has 3 empty column. The rank of B0 is the number of non-empty rows. The rank of B0 is number of non-empty rows. That is equal to 3 because there's 3 non-empty rows. And if I want more information, the rank of C1 is 6 because that's just number of unit I can use to generate one-dimensional chains. And then finally, the rank of C0 is 4 because if you look at the rank is number of columns, number of rows, that is equal to 4, okay? And then this is same as before, rank of C0 is 4. Now, in order for me to get beta 0, remember beta 0 is rank of Z0 minus rank of B0, okay? because rank of Z0 is 4, rank of B0 is 3, so it's 4 minus 3 is equal to 1. What does this tell me? This tells me this simplicial complex has one connected component. But in order for me to actually compute beta 0, I need two matrices because the rank of Z0 coming from matrix sigma 0 and the rank of B0 coming from matrix reduction of sigma 1. Okay. Now, of course, in order for me to compute beta 1, I need two matrices. So I need one more matrix. The one more matrix is a matrix of dimension two-dimensional. The two-dimensional thing in this phase, sigma 2, where the columns are now triangles and the rows are edges. So I have triangle ABC, triangle ABD, triangle ACD, and triangle BCD. Okay. And what are my rows? Can somebody tell me what are the rows in this matrix? This is a boundary matrix, remember?
The edges.
AB,
Yep. AB, AC, AD, BC, BD, CD. Okay. So now the boundary of triangle ABC is AB plus AC plus BC. ABD is AB, AD, BD. And ACD is AC, AD, CD. And BCD is BC, BD, CD. I'm going to do the same thing. I need to reduce this, okay? So I'm going to reduce this to the same way. First of all, I want to keep this first diagonal entry. In order to do that, I'm going to zero out everything below it. So I'm going to add the first column to the second, first row to the second row. I'm going to add the first row to the fourth row. Okay. Now, same thing for this diagonal entry. I need to zero out what's below it. So again, you are going to add the second row to the third row. The second row to the fourth row. And the second row to the fifth row. Okay. So now this is interesting because what I have right now is that the third row now don't have a diagonal entry as what I would like. Okay. So I need the third row and the third column to have a diagonal entry, but I don't have it. And it's not clear I can actually reduce it completely, right? So what I would like to have is I could also do the fourth row added back to the third row, okay? So what do? Basically, I do a swap between the two rows, okay? So I switch between these two rows. So now in order to, I'm going to delete all the ones that is 0, okay, just to avoid. So now I'm going to swap the second row with the third row. So what I get, so I'm going to get this, okay? And now I'm going to keep this last diagonal entry and zero out the rest. So I'm now going to put the new third row added to the fifth row and to the sixth row. Add it to the fifth row, add the third row to the fifth row, third row to the last row, okay? So now I have to do the row reduction. I'm going to do the column reduction. Again, column reduction seems to be easier because I can just add the first column to the second column and I zero out the first entry, second column to the third column and add out this. And then the third column to the last column. Okay, so now what I have reduced this to after reduction is a new matrix. I call that N2. And that new matrix has a looking of 1, 1, 1, and then the rest is 0. Right, if I want to actually, this is how it looks like. So remember again, the number of empty column is going to be the rank of Z2. So the rank of Z2 is now equal to 1, right? Because it's one empty column. And then the rank of B1 is equal to 3 because it's a number of non-zero rows. And then same thing, rank of rank of B1, Z2, rank of C2 is equal to 4 because that's just number of triangles do I have? I have 4 triangles. And then of course, rank of C1, which is number of rows, which is equal to 6, sorry. It's actually 6, okay? So now how do I compute? Remember before the beta 0 is rank of Z0 minus rank of B0, which is equal to 4 minus 3 equal to 1. Beta 1 is a rank of Z1 minus the rank of B1. And rank of Z1, right, from this matrix here, from reduced matrix here, the rank of Z1 is equal to 3. And then from the last matrix, I just do the reduction, the rank of B1 is equal to 3. So that's 0. That means there's no tunnel, no loops, right? No tunnel. And the last one, beta 2 is rank of Z2 minus rank of B2. The rank of Z2, I know from here is equal to 1. And rank of B2 is equal to 0. And I'll tell you why. Because in order for me to get the rank of B2, I need to work with a boundary matrix sigma 3. But sigma 3 meaning that the column has to be tetrahedra, but I don't have the tetrahedra, which means this is an empty matrix. And because it's an empty matrix, the number of non-zero rows is equal to 0. So that's why it's 0. Okay. So now what this means? This means that for the tetrahedra, I have 1 void. Okay. So now we just went through a complete example of how to compute homology by hand. Again, I want to state the fact that computing homology requires reduction of 2 adjacent boundary matrices. But somehow computing persistent homology is just encoded in 1 single matrix operation. Okay. Any questions? Okay. If there's no question, let's move on to our main topic, which we'll see how far we go. This is what I call a revisit to machine learning, but it's from the perspective of classification and from the perspective of training data, testing data, and so on and so forth, and then moving on to kernel methods. So if you have had some machine learning courses before, this will be a brief review. But if you haven't had it, I will also encourage you to do some other reading in addition to today's lecture, because after all, I'm not teaching machine learning at the core of this lecture, but I just rather to give you a flavor of how to kind of understand topological data analysis interface with machine learning. Okay. So when we're thinking about using machine learning, one of the classic thing is classification or regression. And both of those tasks is essentially try to predict things we have not seen by using what we have seen, okay? So for example, if you think about Facebook or Instagram now, is that when you upload a photo, it's going to try to guess who they are, right? Among your friends, they try to automatically label, like, okay, you just took a picture with Tom, for example, and then they will try to find the face of Tom based on your other previous images in the album to say, this is a face of Tom, right? So they try to predict who is in the table, who's in the photo. And when we say predict things that we haven't seen, it's basically the test data, right? Using scene data, the scene data is a training data. So in the photo app, when they predict who is in the photo, the training data are the photos that you have already uploaded to the app before. So they use those photos to try to learn how Tom's face looks like. And then when you say unseen data, is that when I upload a new photo where the model has not seen, is going to try to predict, who that face is. Okay, so that's called test data. So there's two types of prediction, right? One type of prediction is called classification, where we just want to put a label to the data, right? So, I have a bunch of images coming in. I want to say this bunch of images are cat images, those kind of images are dog images. So I want to kind of put labels on them. Or, right, if you think about YIP, or sort of similar recommendation system, is that based on what you have reviewed and so on, is going to try to recommend you, it looks like you really liked Japanese restaurant. Here's a new Japanese restaurant we're going to give you. The other one is, instead of just assigning a label, right, to data, which is usually categorical, there is another thing about regression, but regression is about assigning a value to the data. So for example, based on some known information, maybe there's a new restaurant coming in, you want to predict how much I'm going to like this restaurant based on what they have seen, right? So if I generally have favored to go to Southeast Asian restaurant, and then this is a Thai restaurant that's opened up, then we say, oh, we predict that there's like 95, % of the chance you are going to like this restaurant, right? Something like that. So for classification, it's about trying to get the label correct. And for regression, it's about to predict a value that is not far from the real value, okay? So then there is a corresponding classification accuracy, because I want to see how accurate I can get the label right, versus sort of the error term for regression is to see how far away am I from the true value. So that's where the error comes in, right? So usually in machine learning, the term error is used to evaluate performance. And when error occurs is actually where learning occurs. It's, like when my model is trying to learn something, that's where error might arise. And it's also going to try to train the machine learning algorithm to sort of reduce a particular type of error. So when we say the word training an algorithm, is basically using the training data to learn some prediction scheme that can be used in the unseen test data, right? So the way when we say train is basically using the training data to try to be applicable for the unseen test data. And then in terms of error, right, if I'm talking about a classification, then the training data usually is the one that comes with label. So my X1, X2, Xn are my, say, point cloud, but my Y1, Y2, and Yn are the labels associated with it. So maybe, let's say, if I'm thinking about the most naive scenario, I have a bunch of images. The pixel of each image is converted to a high dimensional vector, and the label is to say, this is a cat, this is a dog, this is a deer, this is a horse, right? The test data is in some sense unlabeled because it's just an image given to you. And then the classification is try to label this new data. So for example, somebody upload another image and you want to say, oh, is this a cat or is this a dog? Or I think 98% time, I think this is, in terms of confidence, 98% I think it's a dog and 2% I think it's a cat, okay? So a classifier, which is a machine learning algorithm, is a function that takes the input, which is a test data, and map it to a label, okay? So this function f, the f of z, is basically the predicted label. And now the training error, which is epsilon train, is basically looking at how many instances where my predicted label is not equal to the actual label, right? So basically, one way to kind of measure is to say that there is a bunch of testing data that comes in where I know what their underlying label are, but I don't tell you ahead of time. I want to use my model to predict the label and to see how accurate I am, okay? So so that's what the training error is. It's sort of, there's a normalization going on to say what is, normalized by the size of my data, but it's to say how accurate is my prediction matches the ground truth. There is what's called a test error, okay? Is how much, right? Is how much for the, okay, so let me be careful here. If you look at my thing, the training error is actually evaluated with respect to the training data, and then the test error is evaluated with respect to the test data. The training error is to say I'm withheld the label of my training labels, which is Y, and I want to see how much do I accurately recover. The test error is only obtained when I know the real label of my test data, okay? So those are two different differentiation. What is a training error? What is a test error? The next one are the other type of errors, right? So regression error is to say how far away am I kind of from the decision boundary. And then the most common ones are things like mean squared error. And errors often in machine learning captures performance, okay? So algorithm usually only knows the training data. So if I just optimize my model or my algorithm for the training data does not guarantee that I'm going to optimize the error for the test data, okay? So sometimes there is a way to define the error. They define it what's called a loss function, okay? And different optimization algorithm optimize for different loss function. So this is a term you're going to see later on when you read the literature in this space. And then there is also the term about what's called underfitting versus overfitting. An algorithm does not use enough information of the training data. That means it's underfitting. And then if it's over adapts to the training data, then it's overfitting. Okay, so those are the situations you want to avoid. And overfitting, I can't emphasize more, overfitting is actually really common problems for some of those models. It's over adapt to the training data. So classification, there's a bunch of classification algorithms. It's essentially identify which set of categories a new observation belongs. So I have a new test data coming in, I want to assign a label to it. And then there's a bunch of classification algorithm. I'm just giving a sample of it, right? Linear classifier, perceptron, kernels, SVM, and neural network. I mean, there's a lot more. But one of the most interpretable machine learning model for a classification task is a linear classifier. And for the next few slides, I'm going to try to explain linear classifier. And I really like the example because it really gives you a geometric understanding of what linear classifier do, okay? So for this example, I'm just starting with a two-dimensional point cloud. And they have some label. The blue is one class, the blue dots is one class, the red star is another class. So let's say I don't know this separation. I just want to find the best line that separate those two classes, okay? And then of course, in two-dimensional point cloud, the separating line is a line actually, but in high dimensional space, we're talking about hyperplanes. But in order to define this separation, I can define this line or this hyperplane by basically its normal vector, which is u. I can define it by a vector that is normal to this hyperplane. And this is generalizable to high dimensions, right? If I have a high dimensional plane, you can always find an orthogonal direction that define the direction, the normal direction of this plane. And then I also, in two dimension, I can also define something which is, the distance to the origin, which is this b vector. And then what this b vector does is tells me how far away is this hyperplane from a frame of reference, okay? And then when you find this hyperplane, points on the same side is assigned one type of label, on the other side is assigned other type of label. For the example, in this case, I would say all the ones on the top is going to assign a label of plus, all the things at the bottom is going to assign a label of minus. Okay, so that's what linear classifier do? But then, what's the limit of linear classifier, right? So for example, in this example, assuming I don't know the linear classifier at the moment. So somebody just give me, 3 points and something like this, okay? And then what's the algorithm for linear classification do is to say, try to find the best fitting hyperplane. Maybe this is a candidate, or not so good. This is a candidate, not so good. But maybe, of course I drew it in I'm going to cheat a little bit. I drew it too not so nice. And maybe this is a good enough one that really separated, okay? But obviously there's a problem. If I have a point cloud like left, there's no way I can find a linear separator between them because it's like they are distributing in a very different way. So this is actually, well, one solution is to get multiple linear separators, okay? So there's two types of solution. Okay, let me talk about, this is actually the motivation why people want to look at kernel methods, is that in the original data space here, they are not linearly separable, okay? And what kernel method do is going to transform this data through a function phi, okay, that map the data point to a new place. And once you do this mapping, it's actually mapped to a space such that the data point become linearly separable. That's what at the root of the kernel methods. It's transforming the data point to a newer space where the operation is easier, and all of a sudden it went from not linearly separable to linearly separable, okay? And of course, there's always, I'm giving examples of linear classifiers, assuming there's two labels. And what if you have multiple labels, right? Then you can apply the linear classifier multiple times. So the first time you separate, let's say my actual label, there's 4 different kind of labels, A, B, C, D. Then the first is I will separate all the points with label A, B from the label C, D. And then for each of the subgroup, I'm going to apply the linear classification. Right? That's one way to deal with that. Now, the second type of classification is called the perceptron algorithm. And the perceptron algorithm actually has a lot of similarities with the linear classifier I just said, because what linear classifier is trying to do is going to try to find a linear separator that kind of reduces the error, right? Basically, it reduces how many different, how many sort of points is wrongly classified if I find a linear separator. So perceptron is basically one of those formalization. The idea is that I start with some random linear separator, and if I think I make a mistake, I adjust the line based on that mistake, okay? So remember I said the linear classifier can be described by a normal vector and plus an offset parameter. The perceptron algorithm is basically, if I want to adjust this linear classifier, I'm just going to push the normal vector in the direction of the mistake, right? If the mistake is positively labeled and away if it's negative labeled. Basically, I want to adjust it so that the wrongly labeled thing is belonging to the correct group. And I'll show you an animation very soon. And one thing that is really at the core of the perception algorithm is actually the notion of inner product. So here is a quick review of what's the inner product between two vectors. If I have two vectors, P and Q, both of them of D dimension, the inner product is basically the sum of an element-wise product of these two vectors, okay? And another way to look into this is that if I take P transpose Q, it will give me this vector, and then this theta is basically capturing the angle between the two vectors. All right. So what does perceptron algorithm do? is try to learn a linear, well, again, I'm talking about binary classification, so there's only two classes. And I'm going to say this classifier is described by a vector, and it's a vector of weights, okay? And right now, I'm just going to, there's another term B, but I'm not going to worry about that. But just thinking about this term, this classifier term W, which is a high dimensional vector. And it's used to classify a sample, okay? So how do I classify it? I'm just going to take essentially W transpose time the data point, and then look at the sign of it. If it's positive, then it's class 1. If it's negative, it is class -1, okay? So this is an example I drew. For example, if I remember this W is basically the normal direction of my hyperplane, right? If I take the normal direction of hyperplane and I take everything that is to the left of it, take any point to the left of it, if I take this normal direction transpose times this point is bigger than 0, and then below it is less than 0. So this is how the classification works. It's by looking at essentially the inner product of my normal direction, which describe my hyperplane, with respect to the points that is on both sides. What did that really mean, this sign, right? This is really a way to judge in high dimensional space whether my current point is above or below, like which side of my point is on, okay? That is really what it is, this sign operation. But now, what is actually pseudocode for the perceptron algorithm? I initialize W to all 0 vector. So, it's some sort of initial direction. And for a fixed number of iteration or until some stopping criteria, for each training example with ground truth, I'm going to look at the current predicted label, right? The predicted label is based on my current classifier direction times the location of the points, right? And I'm going to look at the current prediction. If my current prediction doesn't match my true prediction, my true label, then I'm going to push the classifier in a certain direction, okay? And then this is sort of the update direction. This is just to say, I would like to adjust my classifier so that the prediction of this point is moving towards the right direction to kind of try to reduce my classification error using this training data, okay? So essentially, whenever my predicted, with the training data during the training phase, whenever my predicted label doesn't match the true label, I'm going to shift the linear classifier in a certain direction that is favorable to try to give the right prediction. So what do I mean by that? Like let's say I have current classifier going like this, and at the top is plus the minus. So this point is a wrong classification. So what I want to do is I actually want to shift my classifier in the direction of this data point so that this, in the next step, this data point is correctly predicted. So the best way to actually look at how perceptron works is to have the animation.
The circles are supposed to be above the line. The X's are supposed to be below the line. When the algorithm encounters a point that's on the wrong side of the line, it adjusts the line. In a minute, the algorithm will have the algorithm speed up.
So that's it. That is the
circles are supposed to be above the line. The X's are supposed to be below the line. When the algorithm encounters a point that's on the wrong side of the line, it adjusts the line. In a minute, the algorithm will have the algorithm speed up.
Right. So this is what happened is that each time this green point is doing is looking at, is this one correctly identified? Yes. Then I don't have to adjust my classifier. If this point is wrongly classified, let me adjust it based on the direction I want to move. So as you see the end of this, it actually moved close, right? At the end of this, it's actually moved close to a good classification, a good separation. So now, I just ran out of time, but what I just showed you is how do I adjust this linear classifier in the original data space. And correspondingly, remember, my ultimate goal is to introduce a sort of a kernel perspective. So for the next lecture, we're going to look at a perceptron algorithm to a kernel perceptron algorithm. Okay, so we're going to slowly bring the idea of kernel into place and then set up sort of a few steps to start talking about kernels on persistent diagram. Okay, all right, that's it.